Well, good afternoon, everyone. Welcome to the very last session of reInvent. Very happy to see so many of you stuck around until now. Trust that you've all had a good conference, learned a lot, and hopefully be back next year. So let me start by introducing myself. I'm David Brown. I am the General Manager for Elastic Load Balancing. Been with Amazon for about 7 years, coming up on 7 years. Had the privilege of working on EC2 in the early days, and then moved over to Elastic Load Balancing for about the last year. So I've got some co-presenters today. So Sean Mackley, he's product manager for Route 53. He'll be talking about the Route 53 section of today's talk. And then Paul-Kearney, who is from one of our customers, InfoSpace. He's been with InfoSpace since 2012, and actually led a migration of their data center to the cloud in just 5 months. So in 5 months, they transferred all of their search functionality into AWS and used ELB and Route 53, pretty much all the features we have available for using multiple regions, as well as multiple availability zones. So we'll get to them shortly. I'm going to start off with the ELB section. So welcome to the talk. As you can see, I was late on the slide. Everything fails all the time. You've probably heard Werner say this. It's probably not new. You may have seen it a few times during reInvent. And the idea is not that everything is unstable and going to fail all the time, but that we should actually have at least an approach to availability that says, let's assume that everything is going to fail all the time. A level of paranoia is helpful in designing and architecting highly available systems. So if you start out with that sort of mind view, what you're going to do is make sure that you have no single points of failure in your system. A single point of failure is anything in the system where if it fails, their entire application is going to go down. And with Elastic Load Balancing and Route 53, we provide several components and features that allow you to remove single points of failures in your system. Whether it's making sure that you don't have a dependency on a single instance, making sure that you don't have a dependency on a single availability zone, or making sure even that you don't have a dependency potentially on a single region. Elastic Load Balancing and Route 53 will help you. So let me begin by talking about Elastic Load Balancing. So what is Elastic Load Balancing? Well, to state the obvious, Elastic Load Balancing is a load balancer. It balances traffic across your EC2 instances, making sure that each instance receives the same amount of traffic from your application. Secondly, it's elastic. In the case of Elastic Load Balancing, that means that we'll scale the load balancer to meet the incoming traffic for your application. So as traffic increases, the load balancer will actually scale out in size and scale up in size and be able to handle that load. It's secure. Obviously support HTTPS, SSL. It's integrated. What we mean by that is, integrated with other AWS services. So some of them are CloudWatch, ship metrics via CloudWatch. Auto scaling, together with Elastic Load Balancing, you can automatically scale up and down the instances behind the load balancer. Route 53, which we're obviously going to be talking about today. So integrated into the environment. And it's cost effective. It's significantly cheaper to use an Elastic Load Balancing than run your own load balancing solution on EC2. If you had to stand up a few instances and put a load balancer on there, you'd be paying more than using a load balancer. To give you an idea, it's currently about 2.5 cents per hour, regardless of the size of your load balancer, and it's less than a penny per gig that transfers through your load balancer. And obviously, you have the data processing fee that EC2 charges for outbound traffic as well, but very, very cheap to run. So this is the standard sort of implementation that you see when customers use an Elastic Load Balancer. So in this picture, we've got 2 availability zones, zone 1A and 1B. And we've got 3 instances in each zone. And as you can see on the leftmost side of the slide, you can see we've got an Elastic Load Balancer that's receiving requests from clients. And those requests are being load balanced over the backend instances. And then we actually do support in VPC, Virtual Private Cloud, we do support internal load balancing. So you can actually have a load balancer that will only accept traffic inside your VPC. And that's what we're demonstrating with the second load balancer. So the way we've structured the talk today is we're talking about 3 levels of availability. The first of those levels is instance availability, really making sure that you spread your traffic across multiple instances. And the loss of a single instance is not going to cause problems for your application. The second is zonal availability. So we really encourage customers to use multiple availability zones for all of their applications. So we're going to tell you how Elastic Load Balancing helps you do that. And finally, regional availability. How do you go about deploying your application to multiple regions and making sure that traffic is routed correctly to each of the regions that you might be using? So let's start with instance availability. So it really is the first step that everybody does when they go about making their application highly available. I'm sure you've all seen this diagram. It's probably the first architecture you had for most of your applications. One EC2 instance, you wrote some code, you stuck it on there, and you hit it with a browser. It's probably not the most available architecture that you can have, and I wouldn't recommend anybody go with that. So what you want to do is put a load balancer in front of that. Now we're load balancing over 3 machines. We're still in one availability zone, but what's happening now is the load balancer is accepting the incoming traffic and actually spreading that traffic across those 3 machines, and it does that equally. As I said, incoming request loads shared across the 3 machines. And one thing we haven't spoken a lot about in the past, but it's an important part of elastic load balancing you need to understand is we use the least cons algorithm. And what least cons essentially means is that the traffic is going to be distributed equally across each of those backend machines. Least cons, let's zoom in a little. Least cons will focus on instances that have the fewest number of outstanding connections. So when we send in requests to an instance, the instance that is currently processing the fewest requests will get the next request. As soon as an instance completes a request, it gets the next request. So it does a very good job in smoothing the request load. And the other thing it does very well is reacting to any instance that may have higher latency or slower response times. Because obviously, if it's got a slower response time, it's taking longer to process a request. So as a result, given that least cons sends requests to the machine that has the fewest number currently in process, that machine will just get fewer requests. So even if your instances were different sizes, which I wouldn't recommend you do, the smaller instance would still get fewer requests than the larger instances. Obviously, instances fail, and with elastic load balancing, they can be seamlessly replaced. And this might be an application failure or an underlying EC2 issue. And the way that this works is the same diagram, but now we're going to fail one of these EC2 instances. So as you can see, instance failure happens. It might be EC2 fails or your application has an issue. Elastic load balancing actually has a heartbeat that actually sends requests to your load balancer every couple of seconds. And you can implement either a TCP heartbeat or you can do an HTTP heartbeat. HTTP, you actually write some code to return a 200 request back and says, hey, I'm healthy. And we shift traffic away, and then you can see the remaining instances take that load. So this way, any failure of an instance will automatically be shifted away, and the remaining healthy instances handle the request load. So a couple more details. So obviously, health checks are used to determine the health of the instances behind the load balancer. We do support TCP and HTTP, and you can also specify a port as well as a path for HTTP. You can customize the frequency and failure rate. So you may decide you want to see 1 health check every minute. We do allow down to 6 seconds with a certain number of failures being indicating that the machine should be taken out of service. It's difficult to give you advice on this, but you do want to consider the depth and accuracy of your health checks. Health checks that are very shallow in that they don't go deep into your stack or really assess the health, maybe just turn around to 200. That you may find times where you have situations where your application might be impaired, but the health check didn't really detect it. And sort of the inverse of that, health checks that are too deep, where you're going all the way down to your database or maybe a whole lot of other dependencies, you may find that dependency failures deep within the stack end up taking machines out of service, and you end up with a whole lot of false positives, where you really didn't want to take the server out of service, but because you had a database failure or maybe just a small slowdown on the database side, you ended up taking all your machines out of service. So it's really something that I'd encourage you to think about your initial implementation, and then watch your false positives and your false negatives very, very closely. And when you get them, think about your health check. Did we detect this correctly? Did we miss something here? And then go and edit your health check over time until you find the health check that's best suited for your application. And then obviously, if there are no healthy instances behind the load balancer, so they're all failing a health check, or you don't have any machines behind your load balancer at all, we will return a 503 error back to the customer, or back to the client, sorry. So we've spoken a lot about availability with our least cons algorithm and our health checks. Let's move on to scaling. So by integrating with auto scaling, we can basically adjust the instances behind the load balancer, either scaling them up or scaling them down dynamically, depending on a metric that you choose. So that could be the CPU metric on your backend instances. It could maybe be the surge queue on the load balancer. It could be latency that the load balancer is showing you. It could be a custom metric that you're currently reporting to CloudWatch. So you can use all those metrics and basically decide how you want to scale your fleet. So by way of illustration, we've got a load balancer here with a few EC2 instances. The traffic increases. So this might be, maybe you've got a a video streaming application. Certain times people watch TV, or certain times people shop with your shopping application, like Amazon, and that load starts to increase. So now we want to deal with this. So autoscaling will automatically launch a few more instances, and you can see the load equals out. And the load balancer just seamlessly accepts those new instances, and traffic will now be spread across 5 machines instead of 3. But obviously, that load's going to decrease. That peak is not going to last forever. And when that peak drops off, you want to make sure that you don't waste money. Because now what we're doing is running with a utilization that's too low, so we're actually spending too much money here. So autoscaling will once again watch that metric and see that we've tripped the low threshold, and it'll scale down, and you'll be back to where we originally started. Let's just zoom in on autoscaling a little. So as I said, it automatically scales instances up or down, depending on whatever metric you choose. Custom scaling metrics, I spoke a bit about that. You can literally find a metric that works best for you. It reduces costs. Pretty obvious what it does there. And the other thing it will do that I haven't mentioned is it'll automatically replace a failed instance. So you do have the option to say, if one of my backend instances is failing a health check, autoscaling, please terminate it and add a new one. So it's going to take care of all that management for you. So we spoke about instance availability. We looked at least cons. We looked at health checks. We looked at scaling. Let's move on to availability zones. So I'm sure at this part of the conference, you don't need me to tell you what an availability zone is. I'm hoping you all understand that. But just in case, it's a distinct location, completely isolated from other zones within one of our regions. And as you know, we have 9 regions around the world with 25 availability zones. So we're talking about the white dots on this image. Critically important. Whenever I speak to a customer and I hear that they're in a single availability zone, or I even get the sense from talking to them that they might be in one zone, one of the first things I tell them is, when are you going to move to multiple zones? It's really sort of, the unit of availability inside AWS. We guarantee that no zone will fail for the same reason at the same time, and we work very, very hard to make sure that we can keep that guarantee. So if you have any applications that are in a single zone, and maybe your reasoning is it might be cost, maybe it's complexity of your design, I'd really encourage you to work out how you get to multiple availability zones. Even if it increases your cost a little, it's still going to mean that your application is going to be highly available in some of the worst scenarios. One thing to consider is if you're in multiple zones, you want to consider how many dependencies do you have between your zones. For example, if you're in multiple zones, but you rely on a master database that's in a single zone, and you don't have a good failover scenario, it's really a single point of failure on one zone. Within Amazon, we need to provide guarantee on the isolation between zones. We work very hard to make sure that we have no dependencies between zones. So service teams will implement services that stay within a single zone and don't have any dependencies between these zones. And it's critical for us guaranteeing that the zones remain isolated and highly available. So what I've done here is just taken my original image, which showed the one load balancer with a single zone, and now we just have 6 instances, 3 in each zone. 3 instances of a zone is a good place to be. You don't need to. 2 is okay as well, but 3 is pretty good in that you can lose 1 instance and you're still not down to 1. You can kind of sleep at night if they're 3. If they're 2 and you lose 1, you probably need to get up and launch the last one, because if you lose the next one, it might not be a great situation. So let's talk a little bit about DNS. Each elastic load balancing uses DNS, and each of your DNS records, you'll have one DNS record for a load balancer, and that DNS record will contain multiple IP addresses. I'll expand a little bit further here. So you can see the load balancer's got an IP address on the one side, .1, IP address on the other side, .2, and what your DNS record would serve both of these IPs. The one will come out, return 50% of the time, and the other one will be returned 50% of the time. So clients resolving DNS are going to send their traffic to each one of these zones 50% of the time. And that's the way we basically spread traffic across multiple availability zones. We use DNS round robin, as I just said. That's called DNS round robin, weighted round robin. Where basically, if there are 3 zones, then each one will receive 33% of the traffic. And we rely on clients resolving those IPs and making sure that they don't stick to one IP. Expect DNS records to change. Elastic load balancing will change DNS records when the load balancer needs to scale up. And there's some other situations where you might have an IP changing. What I mean by that is not the domain name, but the actual contents of the records, the A records. So be very careful, or actually don't take your DNS records from ELB and go and put them into a static configuration, whether it's maybe a proxy or a firewall something out there, know that you need to rely on the DNS record. Obviously, I saw a few faces looking at me there when I spoke about clients resolving IPs. Using multiple availability zones does bring a few challenges. One thing we do see is that clients will resolve an IP and then stick to that zone. A lot of Java applications, by default, will just, the first time they resolve an IP, they just say, OK, I got the IP, let's just use that. There is a flag in Java you can set when you start the VM that says re-resolve DNS, don't just keep to the IP. But a lot of cell phones will do this. If you're using a CDN, they often do that as well. If you have a very small number of clients, you might experience what we call zone imbalance. And you can see in this diagram, one of these zones, each one of the zones is receiving different amounts of traffic at different points in time because of the way clients are resolving the IPs. The other problem is you may not always have the same number of instances in each of your availability zones. So in this image, you can see my one zone has 2 instances and the other one has 3. And this, while we recommend maintaining balanced zones, there are periods of time you may have just had an instance fail in one of your zones. And now what we have is one of the zones is taking 50% of the traffic with 2 instances, and the other one's taking 50% of the traffic with 3 instances. And that's not a great place. But that problem's been solved. Last week, you may have seen we launched cross-zone load balancing. That allows you to distribute your traffic across all of the instances in each of your availability zones, regardless of where the traffic came into, which zone the client sent the traffic to. So it solves both of these problems. Now the zone with 2 instances is receiving 1/5 of the traffic on each of those instances, and the zone with 3 is also seeing 1/5 of the traffic on each of those instances. So the fact that you lost an instance in zone 2, really what happens is zone 2 just starts to receive a smaller amount of traffic, as much traffic as it can handle. The other thing it does, your requests per zone, they suddenly become a very thin line. And this was great to see. We had a couple of customers that actually tweeted. One of our customers managed to tweet about 15 minutes after the announcement. It was pretty impressive. He turned it on and immediately seen zones that were seen in balance immediately converge pretty much into a single line. So this makes implementing multi-AZ applications significantly easier. I've mentioned most of the things on this slide. The one thing I haven't mentioned is we will not charge you for bandwidth between zones. As you know, EC2 currently charges, I think it's still $0.01 per gig for traffic between availability zones. If you use an elastic load balancer for this, you will not be charged for any interzone bandwidth, either to or from the load balancer. So if you're talking to an internal load balancer and you end up going to a different zone, you won't be charged for that. And if your load balancer talks to a backend instance in a different zone, you won't be charged for that either. So a significant feature for ELB and something that we're seeing really good results from and hearing good feedback from customers. So that's availability zone redundancy. We see how ELB makes it easy to use multiple availability zones and how important it is that we use multiple availability zones in our architectures. Let's move on to regional availability. So elastic load balancing and Route 53 have integrated and support a single application across multiple regions. I put this slide up before, and now you can see of the 8 regions plus the GovCloud region that we have available around the world, it would be great if we made it really easy for you to host your application across multiple regions and make sure that requests from your customers can be routed intelligently to your applications in these regions. So let me hand over to Sean, who's going to take us through more of the Route 53 details.
Thanks, Dave. So Amazon Route 53, what is it? Well, Route 53 is AWS's authoritative DNS service. We also do something else that's very significant, though, which is we are our own health checking service. I'll talk more in a couple slides about how those two pieces work together for availability for our customers. Route 53 as a service itself is built to be highly available and scalable with multiple layers of redundancy, both in our data and control plane. We serve DNS queries out of 46 locations around the world, for example. And Route 53 also offers a variety of routing tools and health checking tools that allow customers to build their own flexible, high performance, and highly available architectures on AWS. Okay. Route 53 and ELB work closely together. Route 53 provides the DNS service for ELB, for one thing. Route 53 also has the concept of health checks of ELBs themselves. So for every elastic load balancer that is provisioned, Route 53 automatically creates a health check of the load balancer itself. Additionally, that health check then takes into account the health of all of the EC2 instances behind that load balancer to get a view of the entire stack behind that load balancer in a single region. That allows you to treat that region as a single unit of failure or something for availability that you can fail away from. This allows you to build multi-region architectures and backup architectures for higher availability. We call this DNS failover. DNS failover consists of two main components. First is the health checking piece. I talked a bit about how we health check every ELB instance that is launched. We also allow you to create your own health checks in Route 53 of other types of endpoints. So for example, you can health check directly an EC2 instance. You can also health check your own application running in your own data center behind an IP address, for example. We then use the results of those health checks, is this endpoint up or is it down, to drive DNS routing behavior. Specifically, we only vend the DNS answers corresponding to an endpoint that we perceive as healthy. This allows you to build failover into your application. Let's talk a bit about how Route 53 has built our DNS failover feature. First is the principle of constant work. Now, to explain what that is, I'll first talk about what it isn't, or what the alternative is, which would be a work on failure model. That would mean something like, if my application is overloaded, or if there's an outage, I'm going to make a bunch of API calls. I'm going to configure new DNS records, maybe provision new load balancers, launch new EC2 instances. All of those things are API calls that actually have to succeed in order for them to have any effect on the issue that's taking place. As failure may be more widespread in your application, those calls can themselves bunch up in a queue or even fail to complete, compounding the issue and exponentially increasing the time it takes to resolve the issue. Route 53 doesn't do that. Route 53 maintains a constant level of work both in our health checking, so we have the same volume and frequency of health checks whether your application is healthy or down, and same DNS activity. So we continue to serve DNS queries the same way. We don't actually even touch our own control plane when failover happens. There's no API calls involved. And that holds true whether the failure is localized or even widespread. Next, Route 53 checks every endpoint, whether that's an elastic load balancer or EC2 instance, from a global network. We check from within every AWS region, every public AWS region, so 8 regions today. Why do we do this? Well, for your end customers, health of an endpoint doesn't just mean the application is up and running in that endpoint. It also means, as an end user, can I reach that over the internet? Now, internet connectivity around the world isn't always a given. And so we actually develop a composite view from each location that we health check of whether that application is reachable from that location. This becomes particularly important in cases of network partition. So a hypothetical example would be that you're running an application in South America, an AWS region there, as well as one or more regions outside of South America, say US East. Now imagine the case, which can happen, where a large region, say South America, experiences poor internet connectivity to the rest of the world for a period of time. This is a network partition scenario, and in this case, Route 53 is designed to do the right thing for your end users, both inside the partition and out. So, for example, inside of South America, Route 53's health checking fleet, located in South America, will detect your endpoint in that location as healthy. They can see it. From everywhere else in the world, however, they will see that endpoint is unavailable. That health data will then drive how Route 53 and all of our edge locations, those inside the partition and out, will respond to queries for your endpoints. Those within South America will be routed to the South America endpoint. Those outside will be routed to your other healthy endpoint, which is in North America. Next, DNS failover is designed to be entirely automatic, meaning that once you've configured it up front, you've set up your DNS records and any health checks, then the actual failover is completely automatic. No intervention required. It's fire and forget, basically. That failover takes approximately 150 seconds. Now, that number comes from two components. First is we health check at an interval of 30 seconds between health check observations. Then we require 3 consecutive observations to return either failure or health for Route 53 to determine, yes, that endpoint is genuinely up or genuinely down. So 3 consecutive observations will take roughly 60 to 90 seconds. Next, there's 1 minute or 60 seconds of DNS TTL. That is how long that DNS record is cached in the DNS resolvers around the world. We recommend a maximum of 60 seconds for TTLs on your DNS records when you're using DNS failover. So add those up, you get a total of 150 seconds from the time that the endpoint actually fails to the time at which traffic is now flowing to your alternate or backup location. Now contrast that with a more traditional manual failover method where, for example, you're using an external or third-party monitoring service. If it detects failure, it triggers some sort of alarm, could be an SMS, a page, email. That goes to a live person on your team, an operator, could be during the day, could also obviously be during the middle of the night. That person then has to log into some console, manually make some DNS updates, maybe launch new instances. And then, because of their API calls, those obviously have to succeed before they have any effect. Then you have to wait for those changes to propagate. Now you can imagine that in the vast majority of cases, that's going to take a lot longer than 2.5 minutes or 150 seconds. So again, Route 53's DNS failover doesn't touch the control plane at all. There's no API calls involved. Every one of our 46 edge locations is independently pulling the health results from our global fleet of health checkers. Next, you don't have to wait for the API requests to succeed. And lastly, again, it's entirely within the data plane, which Route 53 data plane, we do actually maintain 100% SLA on our data plane. Okay. So let's walk through a simple customer example of how they can easily get started using DNS failover. Let's take a hypothetical e-commerce site. We'll call them example.com. They're running an application stack behind an elastic load balancer, as Dave described, in multiple availability zones in one region. Let's say the customer wants to have a backup in case either their own application goes down across multiple availability zones. We've had customers tell us they're concerned about their own bad software deployment, for example, affecting their app in multiple AZs, or again, some parts of the world having poor connectivity to that region. Very simple solution is to develop a static backup site, something like you could imagine a gone fishing page, fail whale type of page, maintains the company's brand presence online, maybe have an alternate contact method, email, phone number, something to keep the company's brand online even if their dynamic application goes down. How this looks in Route 53 is you configure your primary DNS record to point to your dynamic application behind the ELB. Route 53 will automatically health check that ELB for you. You also configure a secondary DNS record pointing to the static website, which you can host very cost-effectively and reliably on Amazon S3. If the health check from Route 53 to your ELB indicates that your application is up, no traffic will flow to your backup website. However, if the Route 53 health check begins to fail, indicating that your application is down in that region, traffic will automatically be rerouted to that static backup website. Now, a static site doesn't actually have to mean the entire website. If you can imagine a site like Amazon.com, that actually consists of many different components, some of which are dynamically generated for that user, for example, personalized recommendations. Other components are static. Now, for each of these dynamic components, it's possible to create a static backup. So, for example, you could imagine replacing the dynamic list of recommended products for users that have browsed with things that you've browsed with a static top 10 list of top 10 products this week. Right? Each of those components can then be treated as a unit of failure. Okay. Now let's talk about running in multiple regions. Route 53 has made this possible for a while with our feature called latency-based routing. This allows you to actually get physically closer to your end users distributed around the world. The way you do that is run your application in multiple AWS regions around the world. Latency-based routing will then route your end users to the endpoint, to the AWS region that provides the lowest latency to that end user's location. Generally, that corresponds to also being geographically closest, but not always. And so Route 53 actually does measure the internet latency essentially from every point in the world to each of our data centers or AWS regions. And so we will route your end users to the fastest location in terms of internet latency. We have a variety of customers using latency-based routing. One example is in the advertising space of Find Systems. In online advertising for bidding and serving ads, it's important to shave milliseconds off of each transaction to get your bid in faster for the ad. And so Find Systems is one of many customers of ours that are using latency-based routing to run physically closer to those ad exchanges, physically closer to those end users. Okay. Route 53's latency-based routing also has the advantage it's very easy to implement using our API or console, and much lower prices than other traditional geo or directional DNS solutions from many other providers. Okay. This also can give you greater reliability by pairing latency-based routing with DNS failover. So in that case, Route 53 will only route your end users to a region where your application is healthy and is reachable over the internet. So back to the example.com, let's say they want faster page load for customers distributed around the world. So they decide to launch their application in multiple AWS regions. They use latency-based routing to route their end users to the closest region in terms of latency. And then, by turning on DNS failover, they ensure that these end users are only routed to a region where their application is healthy. How this looks in practice is they create multiple primary records in Route 53. Again, because these are elastic load balancers, Route 53 automatically provisions a health check for you and takes that health data into account when you select you want to use DNS failover. In the event that one of these health checks indicates that the application stack is down in a region, Route 53 will automatically shift the traffic that would have gone to that region to the next closest region, again, in terms of internet latency for each end user. These two failover approaches are not mutually exclusive. Quite the contrary. You can combine latency-based routing with a static website backup. And in that case, the static website backup would only come into play if your application were down or unreachable across all regions. DNS failover is quite easy to configure via both the API or the console. For elastic load balancing, it's actually literally one mouse click to start evaluating the health of the load balancer. And then it's just a matter of creating the DNS records pointing to the alternate locations that you would want traffic routed to if this application were down behind that ELB. Now I'll hand it over to Paul to talk about how InfoSpace is using ELB in Route 53.
Thanks, Sean. So I'll share a little bit about our story at InfoSpace and how Route 53 and elastic load balancing helps us to deliver a highly available solution to our customers. InfoSpace has been around for a while, since like the 1900s. And what we do, our primary product is a search product. And the way that we add value, we leverage our relationships with major search engines, Google, Yahoo, Bing, and some others. And for a given search query, we'll submit that query to those search engines, gather all the results from all of them. We'll then combine them, dedupe them, and order them in a way that we think provides value to the consumer. Inject in some of our own custom content, and then return those results back to the user. Our application stack is Microsoft Windows and ASP.NET application. And that search product that I described, we deliver in two different vehicles. One is through a set of search sites, such as dogpile.com, WebFetcher, WebCrawler, Metacrawler. These are sites that we own and operate. We have end users who come to us in their browser. And the other way that we do this is through our search API. So we have distribution partners around the world who want to integrate search results into their website with a way to monetize them. We have an API that they can then consume to get those results. So between the search sites and the search API, there's three different types of users that we see that come to us. The first are the search site users. So these are people sitting at home. They open up their browser. They type in dogpile.com. They're distributed all over the world. And we see about 400 million queries per month that come from just these search site users. The second set of users are the search API partners. And so these are people who are typically operating either out of the cloud or out of a data center. They tend to be more geographically combined, mainly clustered in the US and the EU. And we see about 2 billion queries per month that come from our search API partners. And then the third type of user are what we call click users. Now, these are people who are actually clicking on a search result. The reason that we call these out a little bit differently is if you're a search site user, if you came to Dogpile, a click user is the same as a search site user. But if you're an API partner, the user, when they initially submit that search request, the partner is who touches us. So that's who we're resolving our DNS record against. But as soon as the user clicks on a result, That goes back to us for logging, and then we redirect them onto their destination. So that second request actually comes from a different location than the first request in the case of a search API partner. So the way this looks in our AWS implementation is that we are currently deployed in 4 AWS regions, 3 in the United States and 1 in Europe. And we have multiple availability zones that we run in each of these regions. So if you're a search API partner of ours, you're located around the world. When you connect to us through the CNAME that we give you that's created and hosted through Route 53, you're then routed automatically to the least latent region from your location. Likewise, if you come to one of our search sites, you will also get routed to the least latent region from your location. And then finally, if you're a click user, depending on where you might be, you'll also, when you click on one of those result links, get routed to the region that is the least latent. And the great thing about all this that we've already learned and been able to leverage is that when we find a new cluster of users, maybe a large growth of users in Brazil, we can quickly bring on a new region online, create a new latency-based routing record, and those users will then start to get to use that new region automatically. So when David introduced the talk, he said that we had completed a migration to AWS earlier this year. We owned we had 2 colo locations in the United States. Starting in January through June, we migrated out of those 2 data centers. Our search application now runs 100% in AWS. We're deployed in 4 regions. We currently serve about 4.5 billion requests a month out of AWS. And all of that is run on about 500 EC2 instances behind 50 load balancers and about 70 hosted zones inside of Route 53. This diagram shows kind of our reference architecture. So this kind of depicts what our architecture looks like within one availability zone. And this is our cookie cutter approach. So using Chef and other AWS API calls, we can replicate this very quickly in multiple availability zones or into new regions. So as we were getting ready to do the migration, we were already in these 2 colo locations, and we had lots of expensive hardware gear that helped us do distribution of traffic between our 2 colo locations. And we were a little bit wary in the beginning that a simple AWS API call to set up latency-based routing could actually replace like all this expensive gear. And so we wanted to test that out before we actually put all our eggs in that basket. And so we came up with we already had a way of testing that we called fire and forget, and we leveraged that to test latency-based routing, and I'll walk you through how that worked. So in fire and forget, you have 2 systems. You have your production system, you have a system that's under test. When a user makes a request to the production system, the first thing that system does is it fires off an asynchronous request, looks identical to the original incoming request, and that gets fired off to the system under test. It's done with a very short timeout, so the request is pretty much dropped as soon as it's sent. But then both systems get to process that request. The only difference being that the only response that goes back to the user comes from the production system. So what this lets us do in lots of different scenarios is take traffic that is shaped exactly like our production traffic and put it on a new system and see how it behaves. So when we did this for latency-based routing, we started off with systems in our 2 co-location data centers, and we spun up parts of our search application in 2 different AWS regions. We created some latency-based routing records in Route 53 that pointed to those 2 regions. We turned on fire and forget, and we watched the traffic spin up in both of those regions. And then we killed all the instances in one of those regions. And no joke, 150 seconds later, all the traffic swung over. It was like magic. And it was literally 150 seconds. We could consistently repeat that at 150 seconds. So the results of our high availability experiment in AWS, which is no longer an experiment for us, we can have regional failover in 150 seconds very consistently. We've decreased our latency by 25% to our users worldwide. Route 53 also allows us, in cases where we might be experiencing trouble between a partner and AWS, maybe a network routing problem, we can actually just use Route 53 to route them to a different region. So bypassing the latency-based routing, but instead just point them to a different region until they get their network route sorted out. And in the end, it ended up replacing a whole bunch of expensive network gear from our data centers. So next steps for us are continue to expand into additional regions. And we're also looking at integrating application metrics from our app into Route 53 calls that we might be able to then say, here's an example, if in one region a user comes to us because Route 53 says that that's the least latent, but perhaps we're having network troubles trying to talk to Yahoo to get search results, we might want to influence where those users are actually routed. So maybe not the least latent, because their total experience overall would be better served out of a different region. That's it. With that, I'll turn it back to Dave.
Great, thanks, Paul. So let's just summarize. We spoke about 3 levels of availability. The first of those we said was instance availability. We looked at how elastic load balancing can help you balance your load across multiple instances using least cons as the load balancing algorithm, together with health checks to react to any instances that may become unhealthy, as well as we moved on to zonal availability, where we said, we should not be in one availability zone. Let's make sure that we have our applications in multiple zones. And we looked at how elastic load balancing, together with the new feature cross-zone load balancing, allows you to do that effectively. And finally, as Sean and Paul described to us, regional availability, where you're able to actually run your application in multiple regions and use Route 53 to load balance, to send traffic to multiple of them. So we've been through a lot of content. We haven't shown you too many slides on how to do this. I would encourage you, if you want to know about any of these concepts, it's all documented in both the ELB and Route 53 documentation. So spend some time reading that, and then there are a lot of helpful blogs and tutorials online that will also help you get this set up. Thank you very much for listening. Very happy that so many of you stuck around. We'd be happy to take some questions.